All right, let's talk about uniform circular motion, or UCM. See how the initials make up what we're talking about. The world is not only flat, but oftentimes the motion is not on a straight line. So you got to have some physics to account for this motion that's not in a straight line. Fortunately, there's some easy physics we can use. We can approximate a great deal of non-straight motion as motion along a linear or a circular path. So here's a picture of a circle. It's the radius r. The object is moving around the circle with a constant speed. So it's moving in circular motion. It keeps on moving around and around and around. You know that the distance around a circle is the circumference, and the circumference is given by 2 pi r. And then we have to come up with another definition. Since the object is going to be making the same path over and over again, we want to find out how long it takes to make one rotation around the circle. We call the time it takes to go around the circle once as the period t. We abbreviate it by a capital T to distinguish that from normal time, which is usually a lowercase t. Circular motion is a bit different from linear motion. The object constantly repeats its motion, and it does come back to the starting point. It will repeat itself over and over again. Since the object is constantly changing the direction it's moving, the velocity is not constant, but the speed is. And that's going to be a key point. We define the speed of the object, unfortunately we write it with a v, as the following. The absolute value, or the magnitude of v, is equal to 2 pi r divided by t. The 2 pi r is the circumference, t is the period, so it all makes sense. We usually drop the magnitude or the absolute value signs around the v. This technically is considered speed, not velocity, because speed is the scalar value telling the how much. It does change direction. We'll talk about that in the next slide. So, as I said, the speed will remain constant even though the direction of the motion is constantly changing. You should remember from what we've talked about before that a changing velocity with respect to time is called an acceleration. So if something is moving in a circular path, it is constantly accelerating. This is really, really important and a key fact. The picture to the right shows an object moving around the circle at 3 different times. Notice that the velocity vector is always tangent to the circle. That means if it would stop moving in the circle, it would move in a straight line. That's just an application of Newton's first law. Those red vectors show you the acceleration. If we did some vector math, you would find that the delta v over delta t yields a vector that's always directed towards the center of the circle. Delta v over delta t is a, the acceleration. So for circular motion, the acceleration is always directed towards the center of the circle, and the velocity vector is always perpendicular to the acceleration vector. So they'll always form those right angles there. This type of acceleration is given a special name. It's called centripetal acceleration. The word centripetal means center seeking. So the centripetal acceleration is always directed towards the center of the circle, defining the motion. We also have a mathematical equation for A sub c. A sub c would be v squared over r. A couple more definitions for things moving in a circle. We've already defined the period t as the time it takes for the object to make one complete journey around the circle. The units of t is seconds, or time. F, the frequency, is defined as the number of journeys around the circle made in some amount of time. Mathematically, frequency is equal to 1 over t. So the units of frequency are 1 over s, or seconds to the minus 1, or the best one is hertz. We'll come back to hertz later in the year when we talk about waves. You should also remember that the velocity is 2 pi r over t, and the units of velocity or speed are meters per second. And that the centripetal acceleration is v squared over r, and the units of an acceleration are meters squared, or meters per second squared. So, using the definition of a sub c, v, and f, we can get the following relations. A sub c is equal to v squared over r. If I substitute the 2 pi r over t for v squared, I get the 4 pi squared r over t squared. And then if I use the f is equal to 1 over t squared, I get 4 pi squared r f squared. Which one do you use? It really depends upon the problem. So you have to read the problem carefully, see what the problem is giving you or what it's asking for, and then pick the appropriate value or expression for A sub c. One more thing to be aware about uniform circular motion. You should all remember Newton's second law, the sum of the forces equals ma. You should also remember that n2 is a vector equation, so the direction of the acceleration is the same as the direction of the net force. That means in a problem involving circular motion, some combinations of forces must give a net force directed towards the center of the motion. There is not an additional force in the problem. Rather, one or more of the existing forces in the problem is the cause of the circular motion. So mathematically, we have the following equations. F sub c is equal to ma sub c. That's just Newton's second law. And then if I substitute the different expressions for a sub c, I get the following relations. Again, which one to use depends on what the problem is asking. So we have to read the problems carefully, we have to decide which ones to use, and then we use the appropriate equation. In doing the problems involving circular motion, you're going to use the same procedures we did before, but you're going to replace the acceleration in the problem with the appropriate equation for a sub c. We'll do some example problems in the next few videos. So hopefully this gives you a quick overview of what uniform circular motion is all about.